its reliance on satellite signals, is also its greatest vulnerability. These signals are faint, traveling thousands of miles from orbit. An adversary can easily broadcast powerful radio noise on the same frequencies, a technique known as jamming, which can drown out the satellite signals and leave the missile deaf and blind. This makes GPS unreliable in a contested environment, the very place where it is needed most. It's a powerful tool, but one that can be snatched away at the most critical moment. Radar and optical systems which allow a missile to see its target are formidable. Active radar can pierce through clouds and darkness, but its broadcast is a blazing beacon that screams, "Here I am," to enemy sensors, inviting them to jam it or shoot back. Optical systems, on the other hand, are passive. They just watch, making them stealthy. But they can be fooled by bad weather, smoke, or decoys that mimic a target's heat signature. A flare can draw an infrared seeker away from a jet engine, and a simple smoke screen can hide a tank from a camera, proving that even the sharpest eyes can be deceived. This is why modern missiles are rarely reliant on a single sense. They are masters of fusion, combining multiple guidance systems to cover each other's weaknesses. A missile might use GPS for the long journey, then switch to its internal inertial system if the GPS signal is jammed. As it nears the target, it might activate its radar or infrared seeker for the final terminal attack. This layered approach creates resilience, but it also creates immense complexity, driving up the cost and the computational demand on the missile's onboard brain. The challenge is to build a system that is not just accurate but robust enough to succeed when the enemy is actively trying to make it fail. When we think of diamonds, we often picture glittering jewels, symbols of wealth and romance. But to a physicist or an engineer, a diamond is something far more profound. It is a perfect lattice of carbon atoms, locked together in the strongest chemical bonds known in nature. This structure gives diamond a set of extreme properties that make it seem almost magical. It is the hardest known natural material, an exceptional electrical insulator, and yet, paradoxically, one of the best thermal conductors on the planet, 5 times better than copper at dissipating heat. It is also transparent across an incredibly broad spectrum of light, from the ultraviolet to the far infrared. For most of human history, these incredible properties were locked away in rare, expensive stones dug from the earth. But in the 20th century, we learned to forge them ourselves. Using techniques like high-pressure, high-temperature, HPHT, and chemical vapor deposition, or CVD, we can now grow synthetic diamonds in a lab. These are not fakes, they are atomically identical to mined diamonds. We can grow them as large, thin films or as flawless, single crystals, tailoring their properties for specific applications. We have, in essence, domesticated nature's most extreme material, turning a geological curiosity into a high-tech building block. The implications for technology are staggering. In electronics, the ability to rapidly pull heat away from a sensitive microchip is a critical bottleneck. As processors become more powerful, they generate more heat. A material that can act as a heat spreader, like a diamond film placed under a chip, allows that processor to run faster and harder without burning itself out. This is especially crucial for high-power radar systems which generate immense thermal loads. Diamond's ability to conduct heat while insulating against electricity makes it a perfect substrate for the next generation of semiconductors. In the world of optics, a material's ability to transmit light without distortion is paramount. Most materials, like glass or sapphire, are only transparent to a narrow window of light. But a pure diamond window is a crystal-clear portal for a vast range of wavelengths. This makes it the ideal material for protecting sensitive sensors on the nose of a missile. It can shield a camera or an infrared detector from the searing heat and abrasive forces of high-speed flight, while allowing the crucial light from the target to pass through unimpeded. We are taking the stuff of jewelry and using it to give our fastest machines unbreakable eyes. The United States military, with its focus on maintaining a technological edge, has been quick to recognize the transformative potential of synthetic diamonds. One of the most critical applications is in the heart of its missile radars. Modern active electronically scanned array or AESA radars, like those in the AIM-120 AMRAAM air-to-air missile, rely on thousands of tiny transmit and receive modules. These modules are traditionally made from semiconductors like gallium nitride or GaN. But as the US pushes for radars that are more powerful and operate at higher frequencies to detect stealthy targets, the heat generated becomes a major problem. DARPA, which is the Pentagon's advanced research arm, is funding programs to develop diamond semiconductors as a solution. By using diamond as a substrate for GaN chips, or by creating pure diamond electronics, engineers can dramatically improve thermal management. Raytheon, at its foundry in Massachusetts, is really pioneering this work. The superior thermal conductivity of diamond allows each radar module to be driven at a much higher power, effectively making the radar brighter and increasing its range and resolution. This diamond-enhanced vision gives a missile a better chance of seeing a faint target, like a stealth fighter or a small cruise missile, and provides greater resistance to enemy electronic jamming. It's all about making the missile's eyes sharper and more powerful than the adversaries. Beyond radar, the US is exploring diamonds for something even more revolutionary: navigation without GPS. In a world where adversaries like China can deny access to satellite signals, the ability to navigate autonomously is, honestly, paramount. Researchers at institutions like Lockheed Martin are developing quantum compasses that use a peculiar flaw in a diamond's crystal structure called a nitrogen vacancy, or NV center. This tiny defect acts as a quantum sensor, exquisitely sensitive to magnetic fields. By measuring the Earth's magnetic field with incredible precision, these diamond-based magnetometers could allow a missile, like the Long-Range Anti-Ship Missile or LRA-SIM, to navigate accurately without needing an external signal, making it immune to GPS jamming. Finally, there is the simple brute force advantage of diamond's hardness and transparency.